So in today's lecture, we are going to discuss about curve sketching or how to sketch a curve. Based on whatever we've learned so far, let's try to accumulate our understanding at one place, and we'll be using those ideas to sketch a graph. So we'll be provided with a function f of x. So it could be a polynomial function, it could be a rational function, trigonometric function, or radical function. Whatever be the case, we will start by taking its first derivative. Then we will also find its second derivative as well. Once we have that information, then we will find out its x-intercept and the y-intercept. So x-intercept can be found out by simply letting f of x equals to 0 and then solve for x. And to find out y-intercept, we are going to let x equals to 0 and then find the value of y. So x-intercept and y-intercepts are the points where the curve or the graph of f of x is going to cross the x and the y-axis respectively. Then we can also find the vertical and the horizontal asymptotes. So these are the places where the function blows up. Then we can find out the critical points. So to find out critical points, all we have to do is we take the derivative, first derivative, and equate it to 0. And when you solve for that equation, we get certain critical values. So critical values are the points where the function is going to have some extrema values, such as it could be a maxima or it could be a minima. So which can be determined by using the higher order derivative test. Then after we are done with finding the critical points, we also need to find out the possible points of inflection. The possible points of inflection means these are the points which can be found out by letting the second derivative go to 0 and solving for x. So these are the points which is going to give us concavity. So concavity is a very important concept, and through this idea we can actually check out the rate of change of a function's derivative. Best way to check this: if the second derivative is greater than 0, then we have concave upwards, and if the second derivative is less than 0 or negative, we say it is concave downwards, that the function is going down. Domain is actually necessary. The domain always comes from finding out all the values of x for which fx is defined. Then we can also look for the symmetry. The symmetry could be if it is even or odd or neither, or it could be periodic as well. So these are information that is going to help us sketch the graph. And finally, based on all the critical points and the possible points of inflection, what we can do, as well as the in domain, there's three information which is going to help us construct some test intervals. So using those test intervals, we will be able to approximately sketch the graph of a given function f of x. So let's try it out with the help of an example. Problem number 1. So here we need to sketch the curve of fx equals to x raised to the power of 4 minus 4x squared. So let us begin. First, we'll consider there's the function f of x equals to x raised to the power of 4 minus 4x squared. Then we're going to take its derivative with respect to x. So this is going to give us 4x cubed minus 8x. We'll factorize it. So this will be 4x multiplied to x squared minus 2. Now, from this particular equation, we can find out the critical points. All we have to do is set f dash x equals to 0, and this is going to give us 0 plus square root of 2 and minus square root of 2. So these are going to be the critical points. Next, we find out the second derivative of our function fx. So this will give us 12. So we'll use 4x cubed minus 8x. So we have 12x squared minus 8. So let's take 4 as the common factor. So we have 3x squared minus 2. Then if we set the second derivative equals to 0 and solve this equation, 4 times 3x squared minus 2 equals to 0, we will get the values of x as plus square root of 2 over 3 and minus square root of 2 over 3. So these are going to be the possible inflection points. Also, using our original equation, fx equals to x raised to the power of 4 minus 4x squared. So thus we can factorize as x squared multiplied to x squared minus 4. And if we set f of x equals to 0, then we will get the x-intercepts, which will be 0, minus 2, plus 2. So these are going to be our x-intercepts. Now we'll also try to find out whether these 3 points, that these 3 critical points are maxima and minima, which of them are maxima and which of them are minima. All we have to do is substitute the value of each of the critical points into our second derivative. So if we take 0, then this is going to give us negative 8, which is less than 0. So this is going to be a point of local maxima. For x equals to square root of 2, we will get positive 16, which is greater than 0. So this will be a local minima. Similarly, f prime of negative square root of 2. So this is also going to be positive 16. So that means it is greater than 0. So this is also going to be a point of local minima. Fine. Next, step number 1. So this will be the rise and fall. Rise and fall. Here we are going to check in which region the function is increasing or decreasing. So we will consider the first derivative of our function, and this was 4x multiplied to x squared minus 2. And we had the critical values at negative square root of 2, 0, and positive square root of 2. We'll consider a number line with these 3 critical points. So for negative square root of 2, let's take it as approximately 1.4. We have 0 and positive 1.4. So negative 1.4 is the point of local minima. 0 is the point of local maxima. And 1.4 is the point of local minimum. So we will consider 4x. We'll consider the sign of 4x in all the 1, 2, 3, 4, the 4 regions. Then we'll consider x squared minus 2. And we'll also consider its sign in all the 4 regions. And finally, in the third step, we are going to multiply 4x with x squared minus 2, which simply is our first derivative, f prime of x. So we'll take values less than negative 1.4. So if we take negative 2, so the sign will be negative. For values lying between negative 1.4 and 0, let's say we take negative 0.5, so this will be negative as well. For values between 0 and 1.4, if we take positive 0.5, then 4x will be positive. And for values greater than 1.4, it will be positive. Now, we'll look at the sign of x squared minus 2 for values less than negative 1.4. So if we take negative 2, so negative 2 squared will be 4. 4 minus 2 will be a positive number. If we take negative 0.5, so this will be a negative number. Positive 0.5, this will be negative, and values greater than 1.4, so this will be positive. So finally, we find out the sign of f prime x. So this will be simply the product of 4x and x squared minus 2. So negative times positive will be negative. Negative times negative will be positive. Positive times negative will be negative. And positive times positive will be positive. Fine. So this means here our function is decreasing. Positive sign means our function is increasing. Negative it is decreasing. And positive it is increasing. So this is what the sign of our first derivative tells us. Now we're in step number 2. We are going to check the concavity. So for this, we are going to consider our second derivative. So our second derivative was 12x squared minus 8. And we had 2 inflection points. So one inflection point was negative square root of 2 over 3. And the other possible inflection point is square root of 2 over 3. So we take the number line and we'll consider 2 points on the number line. One will be negative square root of 2 over 3, which is approximately negative 0.8. The other one will be positive 0.8. So let's look at the sign for f double prime of x. For values less than negative 0.8, so we can take negative 1. So if we substitute negative 1 in place of x, this will be 12 minus 8, which will give us a positive value. For numbers lying between negative 0.8 and positive 0.8, what we have here is, let's take 0, then 12 times 0 minus 8 is going to give us a negative number, negative 8. And for values greater than 0.8, we will get positive. So that means in this region, for values less than negative 0.8, we have concave up. For values lying between negative 0.8 and positive 0.8, this will be concave down. And for values greater than 0.8, we have concave up. In the next step, we will combine the results obtained in step 1 and step 2. So let's do that. So we'll consider a number line with all the critical points, the possible inflection points, as well as the x-intercept. So we have the x-intercepts occurring at negative 2, 0, and positive 2. We have the critical values occurring at negative 1.4, 0, and positive 1.4. And we have the possible inflection points occurring at negative 0.8 and positive 0.8. So for values less than negative 2, so for values less than negative 2, we have a decreasing function. So less than negative 2 or less than negative 1.4 will mean the same thing. So here we have a decreasing function, and it will have a concave up. So I'll use an up arrow for concave up and down arrow for concave down. So clearly, if we look at it, for all values less than negative 0.8, we have concave up, and for all values greater than 0.8, we have concave up. So that means here it will be concave up, and for values greater than 0.8, we'll have concave up. And between negative 0.8 and positive 0.8, we have concave down. Now, for values lying between negative 2 and negative 1.4, here we have a decreasing function. So this will be decreasing. For values between negative 1.4 and negative 0.8, so this will be negative 1.4 and 0. Till 0, it is increasing. So we'll consider this as a increasing. So from negative 0.8 to 0, this is increasing. Then we have from 0 till 1.4, this is decreasing. So from 0 till 1.4, it is going to be decreasing. And then for values greater than 1.4, it is going to be increasing. Now, what it means that we have a function that is concave upward for values less than negative 2, and it is decreasing. So it is concave upward. So this is concave upward, and it is decreasing. For values lying between negative 2 to negative 1.4, we still have concave up, and it's again decreasing. In the region negative 1.4 to negative 0.8, we have concave upward, still upwards, but now it is increasing. So this will be concave upward, but it will be increasing. For negative 0.8 to 0, we have concave down, but it is increasing. So concave down, but it is increasing, right? For region 0 to 0.8, we have concave downwards, but decreasing. So this is concave downwards, but it is decreasing. Then between 0.8 to 1.4, we have concave upwards. We have upward concave, but it is decreasing. Concavity is upward, but the function is decreasing. For region 1.4 to 2, we have concavity upwards, and the function is increasing. So this is increasing. And similarly, for values greater than 2, it is increasing. Now what we'll do, we'll combine this, and this is going to help us sketch the curve. So let's do that. So we have at x equals to negative 2 and x equals to positive 2, this is going to intersect the graph here, and so does the graph intersects at a point 0. For values of x lying between negative 2 and negative 1.4, we see that the function is decreasing with a concavity of upwards, and for value lying between negative 1.4 and negative 0.8, the function is increasing but with a concavity of upwards. For negative 8 to 0, it is concave downwards but increasing. And if we complete the picture, this is going to have something of this particular shape. So this is the sketch of our function f of x, which is x raised to the power of 4 minus 4x squared. You can always use a graphing calculator to check that this is what our graph will approximately look like. So let's try it out in another example. Problem number 2, we need to sketch the curve of the function x raised to the power of 4 minus 4x cubed. This time we have x cubed, earlier we had x squared. So there will be huge difference in the shape of the curve. So let us begin. First, we will consider our function f of x, which is x raised to the power of minus 4x cubed. If we take x cubed as the common factor, so we'll be left with x cubed times x minus 4. From here, we can find out the x-intercept, which will be 0, 4. So these are going to be our x-intercept values. Next, we take the derivative of our function with respect to x. So this is going to give us 4x cubed minus 12x squared. If we write it in terms of its factors, so we have 4x squared. So we have x minus 3. So what we'll do, we'll equate this to 0 in order to obtain the critical point. So that will be 0, 3. So these are the critical points. Next, we take the derivative of f prime of x with respect to x, or simply the second derivative of f of x. So this is going to give us 12x squared minus 24x. In terms of its factors, it will be 12x multiplied to x minus 2. So if we equate our second derivative f double prime x equals to 0, then we'll be able to obtain the possible inflection points. So those will be 0 and 2. So these are our possible inflection points. Now, of the two critical points, 0 and 3, we do not know for sure which one of them is a maxima or which one of them is a minima. So what we'll do, we'll substitute this value into our second derivative. So at x equals to 0, f double prime of 0, so this will be equals to 12 times 0 multiplied to 0 minus 2. So this is equals to 0. And we know that whenever the second derivative is 0, so we cannot say for sure if it is a maxima or a minima. So this is a inflection point. Fine. At x equals to 3, f double prime of 3, this will be equals to, so 12 times 3 will be 36, and 3 minus 2 is 1. So this is a positive value. So this means x equals to 3. So this is a point of local minima. So we have a local minima here, and there is no extrema present here. So we'll go to our step number 1. We'll consider f prime of x, and we'll try to find its sign. So we will consider a number line, and here we will have two critical values, 0 and 3. So 0 is no extrema. There is no extrema present here. 3 is a local minima. First, we will consider the sign of 4x squared. Then we'll consider sign of x minus 3. And finally, we'll multiply them. And the product will give us the sign of the first derivative. So for values less than 0, this is always going to be positive because we have x squared here. So for any values of x, this is always positive. For x minus 3, we consider values less than 0. So let's say if we take negative 1, so this will be negative. For value lying between 0 to 3, this is also going to be negative. For values greater than 3, we'll be having a positive value, positive sign for x minus 3. So the product will be, so positive times negative is negative, positive times negative is negative, and positive times positive is positive. So this means that for values less than 0, we have a decreasing function. Between 0 and 3, we have decreasing function. For values greater than 3, we have increasing function. Next, we will consider, in step number 3, we will consider the concavity. For this, we need our second derivative function, which was 12x times x minus 2. So here we had two possible inflection points occurring at 0 and 2. So we will have to consider the sign. So first we will consider the sign of 12x, then we'll consider the sign of x minus 2, and the product will give us the sign of the second derivative. So for values less than 0, which will be a negative number, 12x will be negative. For values greater than 0, it will be always positive. Then we have consider values less than 0. Let's say if we take -1, so -1 minus 2 will be negative. For values lying between 0 and 2, this is going to be negative as well. For values greater than 2, this will be positive. So we'll consider the product of them. So negative times negative will be positive, positive times negative will be negative, and positive times positive will be positive. So this means for values of x less than 0, we have concave up, since this is positive. For values lying between 0 and 2, we have concavity down, will be concave down, and for values greater than 2, it will be simply concave up. So what we'll do, we'll combine the two results and we'll try to predict the shape. So let's do that. We'll also have to include the x-intercepts as well. So our x-intercepts were 0 and 4. So we have 0 and 4. These are the x-intercepts, and then we have value. This is 1, so this will be 2, and this will be 3. Fine. So we'll combine all the results obtained in step 2 and step 3. So for values less than 0, so let's work with the concavity up. So up, we'll use an up arrow, and down, I'll use a down arrow. So for values less than 0, it is concave up. For values lying between 0 and 2, it is going to be concave down. So this is concave down. For values lying between 2 and 3, because for all the values above 2, it is concave up. So this will be concave up. So here we'll have concave up. Now let's talk about the rise and fall. That means the increasing and decreasing nature of the function. So for all values less than 0, we'll have a decreasing function. For values lying between 0 and 3, we'll have a decreasing function. So here we'll have a decreasing, here we'll have a decreasing as well. For values greater than 3, this will be increasing. So that means when we combine these two results, so for values less than 0, we have upward concavity and it is decreasing. So that means this will be the graph. So it is concave upwards, but it is decreasing. For region lying between 0 to 2, it is concave downwards and it is decreasing. So this is the shape of the graph in the region 0 to 2. In the interval 2 to 3, so concavity is upwards, but the function is decreasing. So its shape will be like this. Upward concavity, function is decreasing. Then we have upward concavity, but the function is increasing. Right. So we have the concavity for each of the region. So let's now try to sketch the function. So we'll have 0, 2, 3, and 4. Because we have the function x-intercept at 0 and 4, so it's going to pass through this points 0 and 4. So between 0 and 2, our function is going to, so for values less than, it is going to be concave upward but decreasing. Then it's going to change its direction. Between 0 to 2, it is going to be decreasing, but it is going to have a downward concavity. At 2, it is going to change its concavity. So it is further going to go down at 3. And once it reaches 3, it is going to be concave upwards as it moves towards 4. And for values greater than 4, it is going to be concave upward and increasing. So this is going to be the sketch of our function f of x given by x raised to the power of 4 minus 4x cubed. There was no maximum, we only had a local minima at x equals to 3. So from this picture, it's quite clear that we have a local minima at this particular point where f dash of 3 is equals to 0. So this is how we can obtain the graph. We can sketch the graph. So this time we will consider a new function x plus 1 over x. In the previous two problems, we didn't encounter any asymptote. So this is one where we'll have an asymptote. So let us begin. So first, we consider our function f of x equals to x plus 1 over x. Now clearly, what will be the domain of this particular function? So the domain will be all values of x except 0. So here 0 is excluded because 1 over x, when x equals to 0, this simply blows up. So that means we have a vertical asymptote at x equals to 0. Now, let's check out the nature of this particular function in the neighborhood of x equals to 0. So we have limit x approaching 0 from the positive side. So we have to find out the limit of x plus 1 over x. So this will be equals to limit h approaching 0. So in place of x, we will have 0 plus h plus 1 over 0 plus h. So this gives us simply limit h approaching 0, h plus 1 over h. This will be equals to infinity. We'll have a positive infinity. And when we consider the limit of x approaching 0 from the left hand side, then we have x plus 1 over x. So this will be equals to limit h approaching 0. So in place of x, we have 0 minus h plus 1 over 0 minus h. So this is limit h approaching 0. We have negative of h plus 1 over h, which is negative infinity. So that means when we approach 0 from the left hand side, the function blows up to negative infinity. And when you approach 0 from the right hand side, it blows up to positive infinity. So this is one nature of the graph near the vertical asymptote x equals to 0. Fine. And there is one more thing here. So we have x plus 1 over x. So that means f of x equals to x plus 1 over x. So that means here we'll have, whenever we have a function of the form x plus some other function, then this will give us a slanted asymptote, which will be given by y is equals to x. So we have x-axis and the y-axis. So the y-axis is also the line x is equals to 0. This is the line y-axis equals to 0, which will be a vertical asymptote. And we have a slanted asymptote which passes through the origin. So this is the line y is equals to x. So we'll have to use these two facts to these two asymptotes to construct a derivative. So we have f of x given by x plus 1 over x. So let's try to find out its x-intercept. So this will be x squared plus 1 over x. So when we set this equals to 0, so this will give us x squared plus 1 is equals to 0. There is no such value of x for which this equation is true. So we'll say there will be no x-intercept. So that means our graph of the function x plus 1 over x is not going to touch the x-axis. Similarly, we have to find out the y-intercept as well. For that, we are going to set x is equals to 0. So this will be 0 plus 1 over 0. So this is infinity, so which is telling us that there is no y-intercept as well. So we do not have any x-intercept and y-intercept for this particular function. Let's find out its derivative with respect to x. So this will be 1 minus 1 over x squared. We will set this value to 0, and this is going to give us the critical value, negative 1 and positive 1. So these are going to be the critical values or the critical points. Then we'll take the second derivative with respect to x. So this will be 2 over x cubed. So clearly we see that at x equals to 0, the second derivative blows up. So we'll say that 0 is the possible point of inflection. Also, let's talk about the critical points as well. We have to check out whether if negative 1 is the point of maxima or minima, so is the point 1. So we'll use the second derivative. And in the second derivative, when we substitute x with negative 1, so we have 2 divided by negative 1 cubed. So this is going to be equals to negative 2 less than 0. So we'll say x equals to negative 1 is the point of local maxima. And for f prime 1, this will give us positive 2 greater than 0. So x equals to positive 1 is a point of local minima. So now we will start with step number 1. So step number 1 is rise and fall. For this, we will consider our first derivative function, which is 1 minus 1 over x squared. So let's take the critical values. So we had the critical values -1 and +1. So this was our local max, and x equals to 1 our local min. We'll consider the sign of f dash of x for values of x less than -1. So we can take any values less than -1. This value is always going to be positive. For values lying between -1 to +1, this value is always going to be negative. And for values greater than 1, we will have positive values. You can check that out by taking different values of x. So that means for values of x less than -1, our function is increasing. For values of x lying between -1 and +1, our function is decreasing. And for values greater than 1, our function is increasing. Now coming to step number 2. In step number 2, we check the concavity. For this, we require a second derivative, which is simply 2 over x cubed. We found out that there is one possible inflection point, which is 0. So we'll find out the sign of our second derivative for values of x less than 0. So for values of x less than 0, that means x is negative here. So we'll have a negative sign. For values greater than 0, that means we have positive values. So 2 over a positive x cubed will be positive. So here we have, for values of x less than 0, we have concave down. For values of x greater than 0, we have concave up. So what we'll do? We'll combine the results obtained in step 1 and step 2. So let's do that. So we have our number line. We do not have any x-intercept, so we'll consider the numbers -1, 0, and +1. Now here, let's talk about the increasing, decreasing function, the rise and fall. So for values less than -1, we have an increasing function. For all values lying between -1 and +1, we have decreasing functions or decreasing values. And for values greater than 1, we have increasing. Next, we talk about the concavity. For values less than 0, for all values less than 0, it is concave down. So I'm using a downwards arrow. And for all values greater than 0, we have upward concavity. Right. So this means we have concave downwards. So concave downwards will be a shape of this form or this form, but the function is increasing. So this will be concave downwards, but it is increasing. Then again, we have concave downwards, but the function is decreasing. Next, we have concave upwards. So there are two possibilities, concave upwards. So these are the two possibilities. So we have concave upwards, but it is decreasing. So this is one possibility. And we have concave upwards, but the function is increasing. So this is the possibility. Now we can finally combine this result to obtain the sketch of our function. So we have the x-axis. We have -1, 0, and 1. At x equals to 0, we have the vertical asymptote. Let's call it x equals to 0. And we also have a slanted asymptote denoted by. For values of x less than -1, as we have concavity downward but increasing, so we will get increasing. And for values of x lying between -1 and 0, we have a decreasing function with concavity downwards. Then for values between 0 and 1, we have upward concavity, but this is decreasing. So this is decreasing between 0 and 1. And for values greater than 1, it again has an upward concavity, but increasing. So this is what is the sketch of our graph of f of x equals to x plus 1 over x will look like. So you can use any graphing calculator to verify our result. But there is one more thing. Since this is an asymptote, so that means this value is going to be closer and closer to our asymptote at higher values. So this means this will be closer and closer to the asymptote. Similarly, this one is also going to be closer and closer to the asymptote. So this is how we can sketch the different curve. If we know the inflection points, the critical values, and the x and y intercept, and follow the steps that we talked about.